So I'm going to turn it over to Sandip Patel. He's been with Ruckus 7 years, 7 months, which is basically the whole time. His job is basically to make things work, software level, hardware level. I mean, you're talking to a really smart guy here, and I love him. I'll tell you that. So Sandip, you're up.
Okay. 11AC is sort of the industry buzzword in Wi-Fi right now.
802.11ac is the SDN of wireless.
All right. Okay.
From a buzzword perspective.
So,
Blah, blah, AC.
so I'm going to talk a bit about 11AC, but a lot more about what Ruckus does in that context. Just a brief history of Wi-Fi, really. Every 3 years or so, the Wi-Fi gods wake up and say, oh no, we need to catch up with Ethernet, guys. So, 1997, there was something called DSSS, which is essentially Wi-Fi at up to 2 megabit per second. And then all the way down to 2003, we have incremental improvements. And over that, so at 2.4, and at 5 gigahertz, some guys decided to use OFDM, which is very common in cellular world today. And they decided, well, we can go to 54 megabits using some of the modulations that GT talked about. And that bled over into 2.4 as well. And then 6 years later, the Wi-Fi gods said, oh, you know what, we need to catch up again. So they invented, or just formulated 11N. And that takes us to 600 megabits from 54 using these advanced modulations. A few years later, we have 11AC. And 11AC is going to arrive essentially in 2 waves. First wave takes us to 1.3 gigabits, and that's going to be rolling out probably mid this year, towards the end of this year, from an AP perspective. The clients are going to arrive probably in the handsets around the summer.
Is the difference between those two numbers the difference between channel bandwidth now that the FCC has opened up all that extra spectrum in the middle so that we can get to the 160 megahertz bandwidth?
Yes and no.
Okay.
What's going to happen is, I can talk a bit about that later on, but the first wave of products, this is making some assumptions. The first wave of products are all 3-stream devices.
Okay.
So 3, if you don't, do you know what 3 streams, do you want me to expand on what 3 streams are?
I know what 3 streams are. I don't
So,
know.
okay.
Anybody else?
First wave of products is going to be 3-stream devices. The next generation of chips probably arriving mid next year are going to be 4-stream devices.
Okay.
Okay. So that's where the extra throughput is going to come from.
Okay. So we're waiting on hardware refresh, basically.
Exactly. Yeah.
Okay.
So I was going to talk a bit about the clients. The manufacturer is going to seed the clients capable of 11AC probably around mid this year. I think HTC announced a phone with an 11AC chipset very recently. Okay. Some of the features of 11AC, you've probably all heard about the extra bandwidth. 11N has 20 and 40 megahertz channels. And 11AC takes that sort of one step higher. It's like the 11 on the amplifier. They've gone to 80 megahertz. And there's also an option to go to 160 megahertz of bandwidth. Now in wireless, we need as much bandwidth as possible. GT alluded to that. The more bandwidth, the higher the throughput. We can use lower modulations over a wider bandwidth, still increases throughput. So we're going to see this year devices that will handle these 3 channelizations. And then hopefully next year, towards the end of this year, we'll see devices that can do 80 or 80 plus 80 or 160. The reason I split this out, I did realize 80 plus 80 equals 160 at some point. But the reason I split this out is because 11AC allows 2 different channels to exist at the same time. So 2 different 80 megahertz channels at different portions of the band can exist simultaneously, and the chip will transmit at those both bands simultaneously. That's 80 plus 80. And then the 160 is where that's one contiguous band. The number of spatial streams is also going to go up. I just mentioned that earlier. So the clients that you're going to see in most of the handsets are all going to be single stream. That takes us to around 400 megabits a second, I think. The APs, the mandate for APs is 1 or 2 streams. The Wi-Fi Alliance is still trying to hammer that out as to what the mandatory minimum number of streams is going to be. Ruckus is going to launch a 3-stream product, as most other vendors are. And that'll take us to 1.3 gig. Optional features in 11AC is something called Multiuser MIMO. GT alluded to this. Wi-Fi is like a hub today, where everybody can transmit, and you'll see the collisions occur. Multi-user MIMO turns that into a switch. So we can transmit to multiple clients simultaneously in the same bandwidth at the same time. Right? So that's turning into a switch. And that's sort of borrowed from the cellular world. So the cellular guys are already doing this. LTE has this feature, I think release 10, LTE has this feature already. And what you're seeing is a lot of the cool stuff that's in cellular world migrate into Wi-Fi. GT talked about modulations. We call them MCSs in 11N, 11A speak. The mandatory MCS is 0 through 7, which is taking it all the way to 64 QAM. 8 and 9 are these 256 QAM modes, allowing APs to get to 1.3 gigabits a second. And I'll talk a bit about how Ruckus has distinct advantages in that area. Some of the advanced coding, so what's going to happen is as we transmit these packets, they're going to be smacked on. It's wireless. People are going to smack on it all the time. And there's some advanced coding that's going to go on that allows advanced error recovery. So because the chipsets are scaling up very nicely along with the geometries, we can put more advanced digital signal processing in these chips to have better error recovery. Okay. Something that current 11N chipsets talk about, or can do, is beamforming. Very few vendors have supplied chipsets to do beamforming. Ruckus is one of them. We overlay beamforming on top of our antenna technology. And beamforming allows multiple user MIMO. Okay, so what's going to happen is all the handsets that you're going to see this year are capable of beamforming. They will respond to an AP asking it to give it a certain amount of information so we can beamform to that client. APs will probably roll out next year when 4x4s are going to come. Okay, so I think that's sort of an overall view of what 11AC. More bandwidth, more throughput, and simultaneous throughput to multiple clients at the same time. Okay, that's sort of an overall view of 11AC. When I said more bandwidth, this is what the 5 gigahertz spectrum looks like. So I should have mentioned 11AC is really targeted towards 5 gigahertz. It can be targeted to 2.4, but there's just not enough bandwidth to make it reliable. So in the US, we have approximately 20 megahertz channels. The FCC is going to open up about 195 megahertz more. So that's in the 5.3 to 5.49 band, and then there's about 40, 50 megahertz up here as well. So that's going to allow these 160 megahertz channels to be freely used by 11AC devices. So today what's happening is we're here with 11N. We can bond two 20 megahertz channels together. And what's going to happen in the future with 80 plus 80 is we can bond an 80 megahertz channel here with an 80 megahertz channel over there and transmit in those two channels simultaneously. Okay? And that has some really interesting repercussions for how you pick channels. When you have a multiple AP deployment, if you're transmitting at 80 megahertz here and you have other access points in this, legacy access points in this same channel that can't deal with this, what are you going to do? Okay, so the AC guys the AC tech team really thought about this, and what's going to happen is, somebody mentioned earlier what RTS, CTS is they're going to start transmitting simultaneously in these other extension channels, RTSs, to let everybody know that there's going to be an 11AC frame coming. So everybody, the other access points are going to shut up, essentially. But it's in our advantage to actually spread this as far out as possible so that you can actually multiplex other APs in there. Ruckus has some technology that channel fly. I don't know if JT's talked about this. That can do this dynamically. It will figure out that there's a certain level of utilization in a given channel, and it'll start to move APs just by looking at what the channel is capable of doing, its capacity. Okay. Just a brief word about data rates. And I know in the wired world, there is a sort of minimum concept about data rates. It's one modulation really, DPSK, NRZ. Wi-Fi takes it to a different level. We need extra dimensions when we're dealing with this, when we're dealing with higher throughputs. As I've mentioned earlier, there's 2 new modulations that are going to appear, and we're here right now. We're going to be shipping products this year with 1.3 gigabits of throughput, as are most other 11AC vendors, and capable of getting to here towards the end of next year, I think. But realistically, we'll be around 1.7 gigabits a second with 4 streaming devices. Now, why does our technology have a better advantage at using these higher rates? Higher rates means more throughput, less time on the air. Your packets are not going to less subject to getting smacked by interference. Less time you take. If there's an interferer chopping your packets up, there's 2 views to this. If you take less time, then you reduce the probability of something coming and smacking your packet. Right? Take more time, the chances are it's going to come and smack you. So you can do 2 things. If you take more time, you have more time meaning a lower modulation. You get more robustness in the frame, but you take more time, so you can still be smacked. But it allows the receiver perhaps to use some forward area recovery to fix that problem. The other way to look at that is if I take less time and I use a higher modulation, maybe it's not going to get smacked. It just might get through. So there's 2 ways to look at it. Ruckus algorithms actually use both mechanisms to get that packet to a client. The other things that we do, in order to facilitate MIMO, this is really going to work really well to get these high data rates, is when you use multiple streams. In order to facilitate that, we have polarization diversity. I don't know if you've mentioned that before.
Yeah, a little bit. You can use the big markers, though.
Okay, I thought they were yours. So I
No, you can touch them.
Okay.
I'm going to be your eraser.
I'm not tweeting that.
You seem very close.
There's two dimensions to these antennas. Well, one is vertical, one is horizontal. Vertical and horizontal I can't really draw very well, but let's see if I can draw this better. So imagine a plane like that. This is sort of this way, and vertical would be this way. Okay. Now, when you send these bits in a multi-stream environment, you're going to chop up the incoming 1s and 0s like this. You're going to take this pair here and transmit this pair in this dimension here, and this pair at the same time transmit in this dimension here. Okay, at the same time. So you've got a 0 and a 0 going this way, and a 1 and a 1 going this, horizontal direction, and a 0, 0 in a vertical direction, and these are transmitted at the same time. So what can happen at the receiver is if these arrive together, they're going to smack each other, potentially. But if they arrive in different planes, okay, they're not going to smack each other as much. So you get a better chance of getting these high modulations through. So we're going to couple our antenna technology with this mechanism here, polarization diversity, which we do really well, and we've sort of prototyped this, and get the maximum use out of these guys.
It's kind of interesting. It's similar to some of the DWDM optics, how they get up to 40 and 100 gig. They actually do the polarization, and they filter based on polarization and achieve high data rates.
Right, because you're getting orthogonality in the channel.
So is it just an assumption that with all the mobile devices that everything's going to be 5-10 degrees off?
Well, we'll adapt to it.
Yeah.
Right, so we'll have our antennas can switch in different directions and in different polarizations simultaneously.
Yeah, have you guys in your testing? It's actually just interesting that this Internet of Things is I got 40 different devices that connect via Wi-Fi that statistically majority of my devices will have a polarization of 10% difference between each other as they transmit, or have you tested around this?
We haven't tested around it. In fact, we don't care.
Okay.
Because we'll use the polarization diversity to maximize throughput. So whichever angle it's at, it doesn't matter to us. We'll just adapt and try and use the best set of patterns to that client. So whichever angle, it doesn't matter to our. Okay.
I actually talked to Bill Kish about, hey, why don't we use the accelerometer in all these phones, right? And it can tell us the orientation of it. And his answer was very much like Sandip's, which was, we don't care. We don't care because what the right signals twist actually in midair. That as they reflect, the polarization actually changes. So knowing that isn't as important to us as what's just best.
I think you're misinterpreting my statement here. I was just saying it's novel, and that's something which in the past created a challenge in your RF design, which is the polarization of your antennas and the lack of consistent polarization of your clients. Now it's turned into a method to increase the throughput and availability of your
sorry,
network.
yeah,
Excellent point.
absolutely.
Yeah, excellent point.
Yeah.
Yeah. Yeah.
It's just interesting.
Yeah. It's a good analogy. The DWDM and analogy is very good.
I just tried to take it back to stuff I know.
Okay. So there've been a couple of advances in the Mac layer to facilitate higher throughputs, and one of them is aggregation. Now, 11N had this mechanism of aggregating packets. What that does is it smooshes these 1500 byte packets together and then shoves them off to the client. What 11AC does, it allows, they sort of really looked at real world use cases, really. TCP packets are small, TCP ACKs are really small, not very good for the current forms of aggregation 11N was doing. Because the overhead of putting an encryption layer, encrypting the packet, putting a header on the front of that, sort of is about 50% of a TCP ACK is really wireless overhead. Right? So they took a good look at that and said, how can we make this better? So what they came up with is something reasonably interesting. There's something called an AMPDU, which is essentially a bunch of 1500 byte packets ganged up together like this and transmitted with a single PHY header. And each 1500 byte packet has a little MAC header on it, about 30 bytes. Okay, so this is an AMPDU. And this whole thing is transmitted as an aggregate, okay? So multiple ones, up to 64K can be burst out to a given client. What 11AC does, it says, TCP ACKs are really inefficient when we send them as an aggregate. So what we can do is we have a PHY header, we can have a MAC header that tells it, hey, this is a bunch of small packets. So there's one MAC header now for a bunch of small packets. And then we can have another one, and so on and so forth. It's a bunch of small packets like this. And then we can mix that together with a large set of packets. So we can have a MAC and one packet, which is large, a MAC, another packet, which is large. So essentially, this becomes a mixture of AMPDU plus what they call AMMSDU. And AMMSDU is one of these guys. It's a MAC header with a whole bunch of small packets together. So it reduces the overheads. And when you smack these together, you get a very nice large packet, which can be smacked on by some interference. But in an interference-free environment, you can get up to, this is where all the real throughputs are coming from. You're seeing 1.3 gigabits a second. In the real world, you're seeing about 800 megabits of TCP throughput as a result of this, because we're smooshing everything together, both small packets and large packets. So TCP and TCP ACKs are smooshed together if you're doing bidirectional traffic, and that's really increasing throughput. Aggregate MAC protocol data unit.
Protocol data unit services.
Okay.
We have about, I don't know what else you're going to cover, but we have about maybe 5 minutes left.
Okay, so let me skip ahead to some more interesting stuff. Let me talk about MU MIMO. Today, this is how the real world is. I think there's the yellow color is missing. There's supposed to be 4 streams there. That's there, no. Okay. This is how things are today. It's single user MIMO. So we can transmit up to 4 streams to one client. Okay. When multi-user MIMO arrives, we can split up these streams to multiple clients and transmit simultaneously. So again, hub to switch. This is how things are going to be probably mid-next year. All right. So how is Ruckus positioned to use this? Okay, this makes me salivate. I apologize, but this is really interesting stuff. We're going to use so one of the big problems is how do you schedule this? How do you know that these clients are close together so you can send to them simultaneously? And that's a big problem. LTE guys have spent all kinds of papers written about it. LTE guys have spent a long time researching this because LTE is capable of doing this. They haven't quite managed to solve the problem. But we have one extra dimension. I talked about polarization diversity. We can actually schedule clients that aren't close together.
I'll give you some more space.
So given an antenna, a set of antenna patterns, we can overlay that technology that we have. So now, here's what typical MU MIMO is going to happen. There's a cluster of clients here, okay? And I know, and somehow I know that they're here, and I'm going to transmit to them like this, okay, at the same time, using maybe 1 stream here, 1 stream here, 2 streams here. But what we can do, and there's some issues with this because these guys are going to collide. They're going to cause problems for each other. So what we can do, using our antenna patterns, is actually do this. We don't need to cluster clients anymore. We can transmit to these clients simultaneously using our antennas. Right, so what does that mean? Well, we get more reuse out of the channel, more capacity. Increases our overall throughput. That's what that really means to us. Most other systems, because they can't steer these patterns, they cannot do this. But we can, and we should be able to see very large gains as a result of doing this. And what this really means is more clients, higher client density in our networks. Let's see. Okay, so I think I talked mostly about what the first generation is going to be, and the second generation. The first generation APs you're going to see are going to be challenged somewhat in terms of power. They're going to require, so if you look at some of our competitors.
You mean PoE,
PoE,
not transmit.
PoE.
Okay.
PoE, sorry. What they've done in order to get this 1.3 gigabits of throughput is they've put an extra processor on there. And the radios, if there's 4 radios on there, are going to chew up a lot more power. They're not going to meet AF requirements, potentially. So trying to get a 11AC design into an AF requirement is going to be difficult. Mm-hmm. Ruckus has taken a different tact. We've distributed the processing slightly, and we can meet AF and upgrade our current product to 1782. Can be upgraded to meet with an 11AC card and meet AF as well. Other products you're going to have to upgrade the switching infrastructure to put an AT switch there to power it up. With the 4x4s, it's going to be almost impossible, I think, to meet AF requirements. You're going to need an AT capable switch.
Which means you guys get to sell a bunch more switches or buy.
So something to be aware of. The reason is because more radios means more power. It's very difficult to scale radios as with just process geometries. You can't do it. CMOS won't scale. So that I think the current thinking is that you're going to need AT to do 4x4 11AC. And that's going to happen probably towards the end of middle of next year. Okay. And that's it, I think. Have questions? Okay.
Thank you very much, sir.
Thank you.